Very good afternoon to all. Once again, it is a great pleasure to welcome you all to the day 3 lecture series on mechanical behavior of materials. Once again, I welcome you all to the wonderful forum, and it is my great pleasure to welcome once again our VP sir to this lecture series. Welcome you, sir. Please, you can go on with your lecture, sir.
Is it visible now?
Please, sir, you can go ahead, sir.
Good afternoon, friends. Once again, I'm happy to meet you in the third lecture of the series. Yesterday, we discussed about only the fatigue behavior. Today, we'll discuss about fatigue crack growth behavior. So, before going to the actual fatigue crack growth behavior, once again, I want to recollect what we discussed yesterday for only one slide. So this is cyclic loading. The fatigue behavior, fatigue crack behavior are all depend on the cyclic loading. The cyclic loading means this is a typical fatigue stress cycle. In this, important notations and terminologies are displayed here. So sigma max, sigma is referred to stress here. Sigma max is maximum stress, and the sigma minimum is minimum stress. And the stress range, delta sigma or sigma r, it is given by the difference between maximum stress to minimum stress. And alternating stresses is the stress range divided by 2. That's the alternating stress. That is sigma max minus sigma minimum by 2. It's alternating stress. And then another term is mean stress, sigma m. Sigma max plus sigma minimum. That's average stress. It's nothing but average stress. Then you have the another term called the stress ratio, R, capital R. So it is the ratio between minimum stress to maximum stress. And one more term, it is the amplitude ratio. That is the ratio between the alternating stress to mean stress, sigma A by sigma mean, M. So these are the terms. Why I am repeating is yesterday we discussed in detail about all these terms. What is sigma max, sigma minimum, alternating stress, mean stress, and stress ratio, everything we discussed. I don't want to go again into that. These terms will be useful for the fatigue crack growth behavior also. So what is fatigue crack growth behavior? If you see that the fatigue process, the complete fatigue process, whatever yesterday we discussed, we yesterday we only focused on the stress employed or stress acting on the component, stress acting on the material versus number of cycles to failure. So these two terms only we consider, S and N, that's S and curve, we discussed yesterday. But between this starting point from 0 cycle to a number of cycles to failure, maybe 10 lakh cycles or 20 lakh cycles, or it may be 1 crore cycle. Between this cycle, 1 crore cycle, what is happening inside? What are the stages, whether it is in one stage process or 2-stage process or multi-stage process. So this fatigue process consists of 4 stages. The fatigue crack initiation, the first one is the fatigue crack initiation. It is normally the early development of fatigue damage. But this crack initiation, if you are able to deduct by some means means it is by means of non-destructive testing method, because now we have very excellent non-destructive testing techniques are available today. without breaking, without damaging the component, you can detect any defect is there, this nucleus of defect is there. That also you can find out using ultrasonic testing is there, radiographic testing is there, even the CT, that's computer tomography is there. So many techniques have come now to see that. If you're able to detect this crack, petty crack at the initial stage, then you can remove it, or you can avoid further growth of that crack initiation. So that's why it is called, it can be removed by suitable thermal annealing process, some suitable thermal heat treatment process. You can direct, and you can remove those cracks. The second is slip band crack growth. So if you are not able to, I don't have the facility, or if you are not able to locate the crack because the crack is located on your complex profile. So then what will happen? The crack will grow further, and the crack growth will occur. It's a stage one crack growth. We used to say here in the stage one crack growth. So slip band crack growth. That is the initial crack which is initiated from where it will initiate. Normally in the component it will initiate from many locations. If there is some nano level inclusions, okay, they will start from the nano level inclusions. Even nano level defects, okay, if it is there, then it will start. Even though in metallurgy, in materials, it's very difficult to produce a defect-free component, defect-free material. All the materials invariably will consist of defects, but the defects are in nano level, even in atomic level. So in the atomic level, even the crystal structure, you have a lot of defects. We used to say it is metallurgy, physical metallurgy. We used to tell the point defects, line defects, area defects, volume defects. So if you see all these defects, point defects, line defects, area defects, volume defects, they all comes under the atomic level defects. Okay, so atom level defects. So atom level defects are unavoidable in all the materials. So even from that type of defects, even that atomic level defect, the fatigue crack will initiate. So it is very difficult to locate, okay, identify at the atom level, even by using the non-destructive testing methods. The non-destructive testing method available today can detect up to the micron-sized defect or the near nano-sized defect. Only you can detect by using the technique which are available, radiography or ultrasonic testing. So if it is in the atomic level, it is difficult to detect by the radiography or the ultrasonic testing method. So once the crack initiated from some nucleus, it will grow. Because the cyclic, we are loading the component is subjected to repeated fluctuating load. So that will initiate that will drive the crack to grow further. So that is the second stage, deepening of initial crack on plane of high shear stress. High shear stress, you know that if you apply the pulling force, tensile force, 45 degree to that plane, the maximum shear stress, critically resolved shear stress will act along the 45 degree normal to the applied tensile stress. If you apply tensile stress, okay, it's vertically to that 45 degree, the plane, the plane which is, that plane will have the high shear stress. So the crack will grow along that the maximum shear stress plane. The third stage, once it is initiated and it is started growing in the size of nanometers or micron size micrometer level, then it will grow in the high tensile stress. You can detect after that, even by using a microscope. You can detect, because microscope we can detect in the micron sized crack, even from 1 micron. You can able to detect the crack, and you can monitor the crack, and you can record the growth of the crack. That's the third stage. This is the crack detection, normal to maximum tendencies. Once the crack growth occurred to a maximum level in the component, then the component is separated. The crack means what? It is a separation of one component into two components. Okay, two parts, one part into two parts. Once the crack forms, before crack, it is a unibody. Once a crack is formed, the unibody is divided into two portions, two parts. So if the crack grows a particular millimeter scale, millimeter size, then the component or the material is not able to withstand the load. Even if you apply a load which is lower than yield strength or yield stress, then it is not able to withstand that even a smaller load, then the final failure will happen. So we'll discuss this aspect. This is the four stages of crack, but the first stage you can remove by suitable equipment. So we'll be focusing on the slip band crack growth and crack growth on planes of high tensile stress and the ultimate ductile failure. Right, how the crack initiates. So there are many mechanisms, many metallurgists, they have given a lot of philosophies, a lot of mechanisms. So what happens in the all the mechanisms is pointing that petty cracks are normally initiated at a free surface. Generally, the cracks will initiate from the surface. Why it's from surface? Because surface, we'll discuss at the end of this lecture, we'll discuss surface effect. We used to say surface effect. So, any finished surface, the surface will have ups and downs. Ups and downs means even in the micron level, ups and downs will be there. Even if you do some polishing, super finishing, whatever you do, there will be the ups and downs on the surface. If you measure the surface roughness, you'll get a peaks and downs in the micron scale. So those peaks and valleys, they will act as the stress concentration location, and then from the surface, the crack will initiate. So what happens? The slip lines are formed during the first few torsion cycles of stress. So you know that what is slip is. Slip is a plastic deformation. So the plastic deformation will occur by means of two mechanisms. One is by slip, by twinning. Slip is under the load of the when you apply the load, when the metal get deforms, the metal will deform plastically in the bands. So the bands are called as the slip lines. So the slip lines are formed during the first few thousands of stress, and then the back and forth fine slip movement of fatigue build up notches or ridges at the surface. I'll show in the next slide now. Then those notches, ridges will act as the stress riser, and once they act as the stress riser, then from the location the crack will initiate. Okay, so we'll see that how it happens in the next slide. So this is a small schematic diagram how the fatigue crack will initiate. So this is for one cycle. This is at the top one is one cycle stress cycle I have drawn. It's a handwritten one, and you see that there's the stress cycle is you have tensile stress field at the top portion, top half, and bottom half is the compressive stress field. So this is the specimen which you are holding it. So initially, before loading, the specimen is having a length of 200 millimeter length and 20 mm diameter. Okay, that is the condition at zero. At zero, the specimen, once you load it, before you apply the load, the specimen size is 20 mm diameter and 200 mm length. So this specimen, you are applying a load of stress of 200 megapascal. The stress is maximum stress is 200 megapascal. Maybe this specimen may be a mild steel. Mild steel, you have tensile strength of 300 megapascal. So I am stressing this material well below the tensile strength. So plus 200 to the stress cycle is varying from maximum stress is plus 200 and minimum stress is minus 200. You see what is the variation you get. So the stress increases from O to A, the stress cycle. When it reaches A, the stress cycle reaches A, that is the 200 megapascal, the specimen will get elongate because we are applying a tensile stress. Tensile stress means what? It is a pulling stress. When you pull the specimen, what will happen? The specimen will elongate. The specimen will elongate. When it is elongates, what happens? The diameter is reducing. You see the diameter reduced from 20 mm to 10 mm diameter. At the same time, the length is increased. You see the length from 200 mm length, it has gone to some 250 mm length. So this is for understanding. Okay. So there is when you apply a tensile load, the specimen will deform elastically, and the deformation is the length is increasing and diameter is decreasing. Okay, that is at point A. So now what happens after reaching maximum stress, and the stress comes down to zero, point B, A to B. At B, what happens? The stress is zero. Okay, so that stress is zero. What happens? Again, the specimen come back to its original dimensions, 20 mm diameter and 200 mm length. That was maintained because the stress is what we are applying in the it's in the within the yield point, yield strength, yield stress. Below yield stress only we are applying, so there is no permanent deformation here, only the temporary deformation. So from point B you are applying the opposite, that's a compressive stress you are applying on the specimen. When you apply from B to C, from the stress curve, stress cycle B to C, once it reaches C, you see that the specimen is under compression loading. It's under the compression loading. When you apply when you compress, that is crushing or pushing. Okay, the tensile is pulling and compression is pushing. So when you push it, the what happens? The specimen will bulge. There is a bulging. That's why the specimen is bulging. Bulging means what? It is roughly the diameter is increasing, the length is shortening. Length is reduced and the diameter is increasing. So it is in one cycle. Again, if it comes to zero, again here from C to D, I forgot to put D here. D is the cycle zero, it will come back to again zero. Again, this specimen will reach the initial dimension. So this is in one cycle, okay, one stress cycle, these changes are taking place. O to A to B, B to C, and C to D. Within this, the material undergoes the variation in the under tension. There is inclusion. Inclusion means it is getting intruded. The material is getting intruded, and so diameter is getting reduced, length is increasing. During compression loading, the material getting extruding. It's a bulging. Okay, the bulging is refers to the extrusion. So the intrusion and extrusion repeatedly happening, okay, repeatedly occurring on this specimen because of the repetitive nature of the stress cycle. So this, when you do it many times, lakhs of time, 10,000 times, 1 lakh times, 20 lakhs times, then that area which is in that surface, because of this extrusion and intrusion, the surface ridges will form. I'll show you the next slide. So this is the extrusion. When you apply the compressive load, the extrusion will occur. So extrusion means it's the extruding of this slip bands. So these strips are, if you magnify the locations, the shaded portion, if you magnify the shaded portion in the specimen, okay, the 10 mm diameter here or 40 mm diameter here, if you magnify and see under the microscope, the specimen will look have this type of slip band. So each strip is called as slip band. The slip band is what? It's a deformation taking place along this very narrow region. So there is an ups and there is an ups and downs. So this is the extruded part is here and the intrusion is here. Okay, when you do it many times, 10,000 times, 12,000, sorry, 1 lakh times, so that area, this intrusion area will become, there is a stress concentration. Both extrusion area and intrusion area is stress concentration will occur. Stress concentration means what? If it is uniform, flat surface, the stress distribution is uniform, homogeneous everywhere. But if there is an ups and down like this in the surface, then there is the stress also will vary from one location to other location. So because of this intrusion and extrusion occurs many times, lakhs of time, the particular area which is very intruded, that area is the stress will become the stress concentrated area. From there, the crack will initiate. First, the crack will initiate after some 1 lakh cycles. Once it is initiated, then it will grow in the. So don't think that the crack will initiate from one location. The crack will initiate from multiple locations. There are many locations the crack will initiate. Don't think that is one, not only from one location. The cracks will initiate from multiple. So you will find in the fatigue failure multiple crack failures. Cracks were initiated from multiple locations. Right. So the next stage, once the crack is initiated, the next one is the crack has to grow. Because you are repeatedly applying the stress, you are not releasing the load, you are not releasing the stress, you are repeatedly load is acting on the specimen. So here the next stage, stage 2 is crack growth, stable crack growth. So here what happens, how the crack is growing further. Okay, so for example, so schematically it is explained here. So it is the initial crack. For example, you have a crack 10 microns. The length of the crack is 10 microns. Okay, it's a very sharp crack and very short. Maybe it's a 10 microns length. The length is 10 microns. Okay, when the stress cycle is applied on this is a full component. When the tensile component, tensile stress is applied on this component, what happens? The crack will open up, the tip will be open up because you are pulling. Pulling means what? You are separating. Okay, you are pulling. When you pull it, the crack will become separation. You see the first stage, initial crack 10 micron, and the width, the gap between there is a two surface. When you have a crack, you have two surface, top surface and bottom surface. So the gap between top surface and bottom surface is very small, very narrow. But in the next case, if you see that when it is the from 0 to not maximum, in between this crack opening. Crack opening will start here, and when the crack reaches, the stress reaches maximum point, you see the third one, crack maximum. It is 20 micron. The length is increased from 10 micron to 20 microns because of the tensile load. Okay. At the same time, the gap between the top surface and bottom surface also widened. When you compare the first one and the third one, there is a widening of the gap between the top surface of the crack to the bottom surface of the crack. So, because of the tensile stress, when you apply a tensile component, the crack will open up. When the crack open up, crack length will increase. At the same time, the gap between the top surface and bottom surface of the crack will be widened. So, this is happening up to this maximum load point. So, after this maximum load point, the stress is dropping. Okay, so it is dropping down and it reaches zero. And then here, what happens? You are reversing the stress. Reversing the stress means what? You are pushing it. Compressive stress is applied. You are pushing the crack to close. Okay, so it is starting closing again here. So it is, see the fourth one, the crack closure is occurring here. But at the same time, what will happen? Here you cannot close completely. What will happen? It is from 10 microns, it reaches the 20 microns. But when even if you apply the same amount of compressed load, 200 megapascal plus, even the compressed load, if you apply minus 200 megapascal, the crack will not be closed completely. It is only partially closed. Why it is partially closed? You see that from the starting is 10 micron. At maximum tensile stress, it reaches 20 microns length, crack length. And after the application of maximum compressive stress, it is close to only 15 microns. So how much closed? Only 5 micron length of the crack is closed. Still, there is a increment of crack length from 10 micron to 15 micron. So at the end of one cycle, you will have the increment of crack length from 10 microns to 15 microns. So every cycle will produce this amount of 5 microns or even less than 1 micron, 2 micron increment in the crack length will happen because of the every cycle. Under every cycle, the crack will grow to some. I told you, that so the compressive stress is not completely closing the crack. Why it is not completely closing? Because the reason is because of the tensile stress which you applied in the first half of the cycle, what happens? The material ahead of the crack, it is going into a plastic region. There is a plastic zone around the tip of the crack. There is a plastic zone. Maybe tomorrow we will discuss in the fracture mechanics. So the plastic zone will be produced in the tip of the crack, surrounding the crack. That plastic zone is having the higher strength and higher hardness, unless it is undergoing some work hardening. It is undergoing some strain hardening. So that strain hardening has increased the strength of the material. Because of that whatever you apply the stress to minus 200 megapascal is not sufficient to close the crack completely. So there is a increment of crack. Please understand there is an increment of crack at the end of each and every cycle once the crack reaches the second stage. So this is known as the second stage of the crack growth. So every cycle will produce an advancement of crack. from 10 micron to 15 micron next cycle, 15 microns to 20 microns next cycle, 20 microns to 25 microns. So every cycle will produce, will drive the crack to grow further. So this is happening in the crack growth stage. That's the stage 2. So stage 1 is initiation of crack, and stage 2 is propagation of crack. Okay, so the better thing is under the scanning electron microscope, after the fracture, after the fatigue testing, if you scan the surface, if you scan the surface of the fracture surface of this material, you will find a feature like this. This feature is known as the fatigue striations. This is known as the striations. Why I am showing this the fracture surfaces, because it has relevance to the crack growth mechanism. So you see that there is a ups and downs. Okay, there is ups and downs in the fatigue striations region. What is this ups and down? So this ups and down in the surface is mainly produced by the fluctuation in the load, fluctuation in the stress, which is the stress cycle. So each striation, okay, each striation is corresponding to each cycle. As I told you, every cycle will produce an advancement of crack for a few microns. So this striations is, each striation is the identification of one cycle. So by even you can count the striations and you can tell that how many cycles it has propagated in 1 minute per minute, cycles per minute. You can find out how many cycles it has, the amount it has propagated in one cycle. So this is people sometimes call, this is called the beach marks. The people used to say it is a beach marks. Why it is called beach marks? If you go to the beach, even to the, if you are in Chennai, you can go to the Marina beach, or you are, even if you no need to go to the beach, even the river sand, river bed. So if you walk on the beach or in the river bank in the morning, early morning, around 6 o'clock or 6:30, nobody is there, and if you go for a walking on the sand, you can see overnight wind cause the sand a beautiful arrangement of sand in there. So that sand is, it is not disturbed. The pattern is not disturbed by the people. So you can see the beautiful arrangement of. So it's similar to that type of appearance you can see in the fracture surface of the fatigue. But this striations is produced by single cycle, and you can even measure. You can count how many striations are there. By counting the striations, you can correlate with the number of cycles. Right. So the fatigue crack propagation. So you have stage 1. It is a non-propagating fatigue crack, and the fatigue crack propagation itself. Stage 1 is non-propagating fatigue cracks. In that, you see that per cycle, the advancement of the crack length is 0.25 nanometer. So if it is the nanometer level, less than 1 nanometer, okay, so the crack will not propagate. Even if the crack doesn't, even if you detect the crack, but the crack size is less than 0.25 or less than 1 nanometer, those crack will not propagate further. That's why it is called non-propagating fatigue crack. And the second stage is, it is normally it is widely studied. So stable fatigue crack propagation, widely studied. And third stage, so the unstable fatigue crack, because crack reaches a level, 2/3 of the component level, then it is not able to stand further, the failure will happen. So this is the graph generally curve normally used to plot the crack growth rate versus critical. The y-axis is crack growth rate, dA by dN, and the x-axis is the stress intensity factor range. So here we are not using the term stress here. Instead of stress, we are using a term called stress intensity factor. This stress intensity factor is a fracture mechanics parameter. It is a fracture mechanics parameter. So how this stress intensity factor, what is the stress intensity factor? So it is nothing but K. It is denoted by K, capital K. Capital K is the stress intensity factor. The stress intensity, maybe I will discuss more about this in tomorrow's class, fracture mechanics class. This is K is given by the sigma into root over pi a. Alpha into sigma into root pi a. Alpha is nothing but it is a geometry parameter, because we have different specimen configuration people use here for testing the fatigue crack. So CT specimen, SCNT specimen, CCT specimen. So there are many specimens they use. So each specimen I will have different alpha level. Alpha is a geometric crack. Alpha into sigma into root pi a. Sigma is the applied stress and pi a is the crack length. So it depends, stress intensity factor depends on not only the stress, it is also depends on the length of the crack. If the crack length increases, then the stress intensity factor will increase under constant load. Even the stresses you are maintaining 200 megapascal, but the crack length is increasing from 10 microns to 20 microns, 20 microns to 30 microns. So every crack length will have the stress intensity factor will vary, will increase, will increase. It is called the stress intensity factor is called it's a function of stress range and crack length. We will discuss more about this. And this is a typical petty crack propagation curve. So here now, of course, the graph is not so clear. Anyway, so I'll show another graph later. Next slide. So this is the typical petty crack growth rate. That's a relationship between crack growth rate versus stress intensity factor. So x-axis is stress intensity factor and y-axis is petty crack growth dA by dN. Before going to this graph, I will come back to again this graph. So I want to construct this graph like a S curve in petty life evaluation. So petty crack growth behavior, petty crack proportion behavior. If you want to understand, you need to construct a graph like this. Okay, that is dA by dN versus delta K. You need to construct. Then only you can divide that graph into stage 1, stage 2, and stage 3. And stage 1, it is a non-propagating crack, and stage 2, it is a stable. Stable means you see that the curve is linear. The slope is a constant slope. Slope is constant during the second stage. And third stage, the slope is not constant. It is a variable one because the third stage, the ultimate failure, unstable crack growth will occur. The crack growth speed is not stable and it will lead to the failure. So there are three stages. One is non-propagating, initially stage 1, stage 2, and stage 3. So how they are different? They are dividing stage 1, stage 2, stage 3. In stage 1, the stress intensity factor is very, very low. Stress intensity factor range is very, very low at stage 1. Because of the stress intensity factor is very, very low, the crack is not getting the driving force, required driving force to grow further. Okay, the stress intensity factor is low means what? The crack length is very, very small, very, very small crack. Okay, so if you have a crack of in the nanometer scale, okay, nanometer less, I have a crack length of 100 nanometers, whether it will grow? No, because the crack length is deciding the stress intensity factor. The stress intensity factor is the energy required for the crack to grow. If the energy is not sufficient, okay, the crack will not grow. When the energy will not be sufficient, the crack length is lower. Okay, even if you have a stress applied, what is the stress you apply? The crack length is not sufficient, then it will not grow. So that is the stage 1. Stage 2, once it is now slowly it reaches stage 2, the stress intensity factor range is sufficient to drive the crack at a constant speed. Constant speed. In stage 2, you see that the crack growth rate is linear. It's linearly varying. The slope is constant everywhere. So that is called the people used to say this the Paris regime. Paris means it's a fracture mechanics scientist. He developed the equation for defining that stage 2 crack. So that's why it's a dA by dN into A into delta K power M. That's the equation proposed by, it's not A small a, it's a C, it come as a C into delta K power M. So for this linear region, this equation is proposed. What is the dm by dn? It is the y-axis, y, and the a is, it's not a, it is a capital C, it's a mistake. C is what? It's the intercept of the curve, and delta k is x-axis, x, and m is the slope of this curve. Slope of the curve is dy by dx is the slope of the curve. We'll see that later. Right. So if you want to construct this fatigue crack growth curves, then you need to have a facility like this, instant fatigue testing machine. So we have this machine, servo hydraulic fatigue testing machine. You can hold the specimen is held here. Two pictures are there, and there is the specimen was held here, and this is the specimen. On the right side you can see. So this the crack is introduced already. We are Mechanically, we are introducing a crack, a small, very, very small crack. Then we are applying the stress, okay, fluctuating stress. Then the crack length is, the crack growth is monitored using a web camera, which is kept close to that. And from the web camera, it is connected to a computer. The computer will record the crack length. So now nowadays, advanced techniques have come, like acoustic emission techniques have come to monitor the crack initiation and crack propagation. A lot of techniques have come. This is one technique which we are using to measure the crack growth. Okay, this is a specimen. It is a one type of specimen. There are many specimens there. Tomorrow I'll tell you in the fracture mechanics. So this specimen we use normally CCT, central crack tension specimen. So it is in the center. You see that there is a crack, 6 mm. The crack is machined by using wire cut heating process. Because mechanically we are introducing a crack. Otherwise, no, if you don't introduce a crack, if you test the specimen, the crack will initiate from anywhere. And it's very difficult for us to monitor the crack or locate the crack or identify the crack to the symptom. So what we do, we introduce a crack of the length of 6 millimeter. The total width of the specimen is 30 millimeter. Okay, so this crack is machined using wire cut EDM process. Sharp crack is introduced, machined using wire cut EDM process. Then the specimen is held. You see that in the specimen is held like this, and the stress is applied, and you can monitor the crack from the both the tips, from the both the side of the crack tip. You can measure how much it is taking for every 1 mm cycle. So the typical static crack propagation data sheet. So when you do the test, you need to have a data sheet like this. You have to prepare what this data sheet is having. You have crack length. So the first column is crack length, and second column is number of cycles. And these two is very important. First two columns are very important. The other columns are derivative of the first two columns. So crack length is small a, normally denoted by small a, and number of cycle is capital N. So what is the change in crack length? So you see here, the crack length is increasing from initially starting point. You see the specimen is 6 millimeter crack length. From 6 millimeter, it has gone to 7 millimeter. How much time it takes? It takes 10 lakh cycles. After 10 lakh cycles, the crack has grown from 6 millimeter to 7 millimeter. So for the next one, 7 millimeter to 8 millimeter, another 1 mm. Okay, it has taken from 10 lakh cycles to 17 lakh cycles, and 8 to 9, 25 lakhs. So like that, you measure the crack slowly and find until it fails, the specimen fails, you record the number of cycles. Okay, every 1 mm you record what is the number of cycles, how many cycles it takes for. So then it is changing. DA is what? Change in crack length. A is crack length, DA is nothing but change in crack length. What is change in crack length? From 6 to 7, the change is 1 millimeter. 7 to 8, 1 millimeter. So up to 10 to 11, it is 1 millimeter. 11 to 32, 35. So here after this, no, the crack will grow faster. After the 13 mm crack length, the crack will grow faster. You see that 42 lakhs, 46, 48, 49, and to the 49.5. So it will grow faster. So we are measuring at 2 mm interval. So that is DA. What is DN? The change in cycle. Okay, 10 to the difference between 10 and 17. Okay, sorry, it's a small mistake here. So you forgot about this data. So here you are getting the change in number of cycles. You are getting 10 lakhs, 5 lakhs, 3 lakhs, 2 lakhs, and it is getting reduced. It is starting 10 lakhs from 6 millimeter to 7 lakhs, and then it is reduced to 5 lakhs, 3 lakhs, 2 lakhs. So when the crack grows, the number of cycles, change in number of cycles is getting reduced. So this ratio, DA by DN, that is called you divide DA, 1 by 10 lakh is 1 into 10 power 6, 1 by 5 lakhs, 2 into 10 power 6, 1 by 3 lakhs. So you divide that is the crack growth rate, DA by DN. So DA by DN, the unit is mm per cycle. In one cycle, what is the increment in crack length? Okay, that is the DA by DN. In one cycle, what is the increment? Because in every cycle, it is difficult to measure the crack length. You are taking 5 lakh cycles. It is the material is taking 5 lakh cycles for 1 mm increment. So 1 by 5 lakhs is in one cycle. What is the crack length increment? 2 into 10 power 6 minus 6 millimeter. So that is the dA by dN. Okay. So then you are applying a load, maximum load and minimum load stress you are applying. So find out what is the maximum stress intensity factor. So maximum stress intensity factor, as I told you, the formula is there, alpha into sigma into root pi A. So you know the stress. Suppose you are applying 200 megapascal, you know the stress. And crack length 6 millimeter, you know that. Pi, you know that it's 1222 by 7 is a pi, 3.14. You can get the values of the K by using this formula. Using this formula, you can get the value. So K max is the maximum stress intensity factor. You apply maximum stress here. Here to calculate the minimum stress intensity factor, you apply the minimum stress. And then the difference between these two stress is the stress intensity factor range, that is the dk, delta K. So you have to relate now, draw a graph between dA by dN, okay, that is the 1, 2, 3, 4, fifth column versus the 6, 7, 8th column. You forget about other column now. Okay, so the fifth column versus the eighth column. Fifth column is dA by dN, crack growth rate, and last column is the stress intensity factor range. So using this, you have to draw a graph. Okay, so before drawing this, if you see here, this is drawn between the crack length versus number of cycles. So it is, if you see here, crack length versus number of cycles. If you draw a graph between these first two columns, you will get a graph like this. What is this? You have different crack length because it is for the, it's one of the test results we carried out in our center on a ferritic stainless steel. So you see that stress range is only 100 megapascal. The crack length is, initial crack length is, we introduced a crack length of 5 millimeter starting point in y-axis. So here it is 0 cycle. And at the application of cycle, the stress cycle, you see that the crack is going. Each one is for a specific joint. So this is the first one is for GTAW, the green one is for the laser beam welding, and the purple color is for the electron beam joint, and the FSW, the last one, and the base metal. Base metal is in blue color. Okay, so you can construct this type of crack. This curve is called crack growth curves. And from these curves, you have to find out, as I told you, from this data. Okay, so the fifth column, dA by dN data, and the last one, stress intensity factor data, you can plot like this. You can plot like this. So y-axis is crack growth rate, and x-axis is stress intensity factor range. Okay, so what are the data here we are plotting is, this is for the welded joints. Okay, so the welded joints, as I told you, the maximum limit is you can test up to 2 into 10 power 6 cycles. So this is, there is no 1 into 10 power minus 7 and all will not come here. So what do you infer? What is the importance of this constructing this crack growth rate for FCGR, fatigue crack growth rate, and let's say F range. So these, you have to find out slope of the curve. Okay, slope of the curve is M. You have to find out for each curve, you have to find out what is the slope of the curve. And for each curve, you have to find out what is the intercept of the curve, C. So any equation, why, if it is, because it is drawn in the log sheet. In the linear scale, you draw it in the y equal to mx plus c. Okay. So, but in the log sheet, it will be power equation. So, this is in the power equation. Y equal to x power m into c. X power m into c. The x power m is the slope of the curve, and the c is the intercept of the curve. Okay, those two things you have to derive from this graph. And another thing is, there are two design parameters also we will derive from this graph. So we will take as criteria as 1 into 10 power 6. At 1 into 10 power 6 minus 6, 1 into 10 power minus 6 cycle, what is the stress intensity factor for this? For example, the last one is FSW joint, friction stir welder joint, the maroon curve. For this, what is the stress intensity factor range at 1 into 10 power minus 6 cycle? It is 8 it is coming. 8 is 8 MPa root meter. So this is called as the threshold stress intensity factor. I will come back to the why it is called threshold stress. Similarly, you can take the, sorry, I'll go back. Yes, 10 power minus 3. 10 power 1 into 10 power minus 3. Draw a horizontal line parallel to the x-axis where it intersects in the each curve. For FSW, it intersects somewhere around 4. That is 4 means 40. 1, 10, 100. So 4 means it's a 40. So 40 MPa root meter. That is called the critical stress intensity factor. Okay, there are two stress intensity factor. One is the threshold stress intensity factor, and the other one is the critical stress intensity factor. Threshold stress intensity factor is the lowest level of stress intensity factor, and the critical stress intensity factor is the higher side of the stress intensity factor. So both will have significance. So below this delta KTH, that is called threshold stress intensity factor. If the stress intensity factor is lower than that value, for example, 8 MPa root meter. Okay, 8 MPa root meter is the delta KTH, threshold stress intensity factor. If stress intensity factor is lower than this value for FSW joint, the crack will not grow. Okay, that is the threshold. So if the crack has to grow, then the stress resistance factor has to reach 8 MPa root meter. Okay, if it doesn't reach 8 MPa root meter, then the crack, even the crack present in the material, it will not grow further. Similarly, in the 10 power minus 3, 10 power minus 3, whereas y-axis you see that 1 into 1 e power 3 minus 3, and that point, draw a parallel line, horizontal line, parallel to the x-axis. Where it intersects in the maroon color curve, it intersects somewhere here at pi. Okay, pi means what? 50, 10, 20, 30, 40, 50. So 50 MPa root meter. That means what? Critical stress intensity factor. Why it is called critical stress intensity factor? Up to that stress intensity factor, the crack will grow steadily. Stable crack growth will occur. Above that point, above 50 MPa root meter, the crack will be unstable crack growth will occur. Unstable means you cannot measure, you cannot monitor. The crack will, the failure will occur anytime. So we should, these two will be the fracture mechanics parameters for fatigue, threshold stress intensity and critical stress intensity. Below threshold stress intensity, it is safe. Above critical stress intensity, it is unsafe. Between threshold to critical stress intensity factor, the crack will grow steadily. Stable crack growth will occur. So this data are, most of the data are belongs to that region. That region is the Paris equation. So from this curve, we can get these data. Okay, each curve for base metal, FSW, EBW, MW, GTW, see the crack growth exponent. M is the slope of the curve, and C is the intercept of the curve. And threshold is stress intensity factor at 1 into 10 power minus 6 cycle. Normally, for unwelded material, this they will not take 1 into 10 power minus 6, they will take 1 into 10 power minus 7, 1 into 10 power minus 7 cycle. Because this is a welded joint, the welded joints will have defects, okay, micron level defects in the joint. So they are giving a consideration for that. They are taking the higher level. So, but unwelded metal, normally they use threshold resistance factor is 1 into 10 power minus 7 cycle. That means 1 crore cycle. Okay, yesterday also I told 1 crore cycle. So here also it is 1 crore cycle. This is welded joint. That's why we have taken 1 into 10 power minus 6 cycles as the and here critical stress intensity factor 1 into 10 power minus 3 mm per cycle. Okay, mm per cycle. See the values. These values will differ. So the threshold, if you see that for GTW it is 5 megapascal MPa root meter. For FSW it is 8 megapascal. That means what it says, the in the FSW joint, even if it reaches 7 or 7.5 megapascal root meter stress intensity factor range, the crack will not propagate. But in GTW, even if it reaches 5 MPa root meter, the crack will propagate. So threshold means from the threshold stress intensity factor, that's the minimum stress intensity energy that is required for a crack to grow. Threshold means, please understand, this is a minimum energy that is required for a crack to grow further. That is the minimum. That's why it is called threshold value. If you have a below threshold, threshold means like a pass mark. So you have to score 50 marks to pass. Okay, that is the threshold point. Above 50, you have different classes. But if you don't, even if you get 45, okay, because you are still failed. Okay, like that, this is the minimum energy required, the stress intensity factor required, then only the crack will grow further. Okay, so in this point, critical stress intensity factor is once it reaches that value, then the crack growth will occur very quickly, very fastly, unstable crack growth will occur here. Okay, this is something related to this curve again. Now I'll go back to this graph, then understand, you can understand now. So in the stage 1, the threshold, the stress intensity factor range is very, very low. And in the stage 2, it has reached the threshold value, and then it is taking the constant steady growth. And this the third stage, it's unstable crack growth, that is the critical. So between the starting point of stage 2 is delta KTH. Okay, delta KTH. You see that the mark arrow is put here, delta KTH. And similarly here, the end of stage 2 is the delta K critical. So between delta KTH and delta K critical, the crack will grow steadily. There we can apply this Paris equation. The Paris equation, the power equation is called as the Paris power equation. That can be applied only in this second stage, not on the first stage, not on the third stage. It is not applicable. And this equation is given here, dA by dN equal to A into delta K for M. Some books, they use A, instead of A, they use capital C to avoid the confusion with the crack length. So they use capital C. So that A is A or capital C, whatever it may be, it is intercept of the curve. And M is the slope of the curve. So if you know slope of the curve, M, and if you know A, and you know the stress intensity factor, okay, stress intensity factor you can calculate. If you know the crack length, if you know the stress, what is acting on that, you can calculate delta K. So if the right side component is known, once for this M and C is a material property. It depends on material. Okay, it is for aluminum, M value is different. For stainless steel, M value is different. For titanium, M value is different. And C values are different. It is material dependent, structure sensitive property. Even if you change the structure, there will be a change in the M and C values. Okay, by substituting in that M and C value, you have to evaluate for new material. For old conventional materials, this M and A values are available in the handbooks. For new materials, for new processes, you need to evaluate M and C and substitute in this equation, and you will get dA by dN. dA by dN is what? It is the crack growth rate. At what speed the crack will grow. And then the final, the life also you can evaluate by integrating from zero crack length to final number of cycles. You can integrate and you can get using this formula, final crack length, initial crack length, and these values. By substituting that, you can calculate you can estimate the fatigue life. So I'll take another 10 to 15 minutes. So this is the factors. What are the factors influencing the fatigue behavior? There are many factors, as I told yesterday. Stress concentration is one factor. Size of the specimen is one factor. Surface characteristics another factor. And there are metallurgical variables. Corrosion is one factor. Temperature is one factor. Combined stresses are. We'll see what are the time formats. We'll see some of the effects of these parameters. So stress concentration and fatigue. What is stress concentration? There is, if you introduce a notch, or if you mention a keyway, or if you mention a slot in the component, that will introduce a stress concentration surrounding that keyway or slot or notch, whatever you introduce, that will introduce a stress concentration. If stress riser is higher, okay, stress concentration is more, obviously the fatigue strength will be higher. Fatigue strength will be lower. Okay, fatigue life will be lower because already it's, you are introducing, you are giving a provision to crack to initiate from your location. Even if it is not there, it will initiate. It will crack to initiate. We have seen the mechanism, but you are introducing. Okay, there is no other way. I want to fix a pulley. I want to fix a gear. I want to fix one bolt. So then I have to make a drill. You have to make a hole. I want to make a slot, a keyway. So when you do like that, definitely there will be a stress concentration. So that stress concentration you can calculate by using theoretical stress concentration. So if you see that graph, SN graph curve, there is one is the top curve is unnotched specimen. For unnotched specimen, you are getting a curve like this. That's a higher strength. Okay, fatigue strength is higher. You take 10 power 6 cycle. Okay, 3, 4, 5. Yeah, 10 power 6 cycles. The stress is what? What is the stress is something around 600 megapascal. But if you introduce a notch on the same material, the fatigue limit, endurance limit, is come down to 300 megapascal, only 300 megapascal. The horizontal line, you see the horizontal line and the corresponding horizontal line, you find out what is the stress in y-axis. Okay, you have to relate that. So for a notch specimen, the fatigue limit fatigue strength is only 300 megapascal. Okay, for unnotched specimen, the fatigue strength is something around 600, just above 600. It will be around 650 megapascal. So if you don't have notch, the the material is having fatigue strength of 650 megapascal. But if you introduce a notch, that reduces the fatigue strength to only 300 megapascal. Okay. So why it is reduced? Because of the stress concentration that is caused by the notches. The stress concentration causes the notches. So here there is a notch sensitivity, whether the notch is sensitive, whether notches are sensitive always, whether it is highly sensitive or less sensitive. Okay, how will you calculate? There is a notch sensitivity factor Q. Q is introduced here. The Q you can calculate by Kf minus 1 by Kt minus 1. What is Kf? Kf is fatigue notch factor. Kf is fatigue notch factor. Fatigue notch factor is what? It is a ratio of fatigue strength of notched specimen and divided by fatigue strength of unnotched specimen. Okay, so you have to find out. So you have to find out this. I told no fatigue strength of notched specimen is 300 megapascal. Fatigue strength of unnotched specimen is 650 megapascal. The ratio between these two is called as the fatigue notch factor. Okay, fatigue. What is Kt? Kt is theoretical stress concentration factor. Theoretical stress concentration factor. You know the formulas. It is normally it will vary from 1.5 to 2.5. But we can calculate what is the maximum stress and the average stress. The ratio between maximum stress to average stress is the theoretical stress concentration. So if you know Kf, if you know Kt for your specimen, for your notch, for your thing, then you can substitute here and you will get the Q. If Q value is lower, 0.1, 0.2, 0.3, then the sensitivity is less. Effect of notch is less. But if the Q value is higher, 0.7, 0.8, 1, towards 1, it will not exceed 1, towards 1, 0.7, 0.8, 0.9, then the sensitivity is very high. Okay, so again the notch sensitivity is the material parameter. For each material, the Q value will differ, and one need to evaluate the Q value to understand the notch. Okay, so size effect. Another one is the size effect on the fatigue. Size effect means because most of the fatigue data we generate in the labs. In the lab, we are using a standard specimen. The specimen size is restriction. There is a limitation. It's not the actual. Though it is simulate the actual specimen, the size is small. So whether this data, whatever you generate in the lab, is applicable for the industrial scale. Okay. So if you see here, this experimental scale is not equal to industrial scale. So the problem is fatigue property is better in small size specimen. Okay, smaller specimen, the specimen is smaller, fatigue strength will be higher. If the specimen is larger, then the fatigue property is lower. Okay, larger specimen. Why it is? Larger specimen increase the surface area. First one is surface area. So you have to, for just example, you take. I have a specimen which is having 10 millimeter diameter. Okay, I have a specimen, another specimen, 100 millimeter diameter. What is the difference in these two specimens? I can test 10 millimeter diameter specimen in the machine. I cannot test 100 millimeter diameter specimen in the machine, the testing machine, because the capacity of the machine is limited. But what is the difference? The surface area of 10 millimeter diameter specimen is very, very small surface area. Okay, and for 100 diameter, the surface area is very large. So if the surface area is large, then there is here the stress gradient across the cross section. Stress gradient across the cross section is large. There's large variation across the cross section. From the outer surface to the center of the specimen, the stress gradient will be large. So large amount of material, higher volume of material is under stress in the large size specimen. Small specimen, the stress gradient is very less. It is varying from center is what? At 0 to 5 millimeter. Outer surface is 5 millimeter only, within 5 millimeter. But here 0 to 50 millimeter. In 100 diameter specimen, it is 0 to center point is 0. The radius is 50 millimeter. Then only you will get 100 dia. So 50 millimeters. The stress will vary from 0 to 50 millimeter. But in the small specimen, it will vary from 0 to 5 millimeter. Understand? So this is because of this variation, the large volume of material is stressed in the large scale, large specimen. So the fatigue strength will be reduced in the large specimen. So they use the size factor. So even when you do at the lab scale, they'll test at small specimen and they'll use like a factor of safety. There is a size factors are there. They will apply the size factor and they will divide this fatigue strength for the large size specimen. What is surface effect? Yes, surface effect is another parameter that is it's very sensitive to surface. As I told you, most of the cracks, surface fatigue cracks will initiate. Most of the time will initiate from the surface only. Only in few occasions it will initiate from the inner side. If you have intrusion, if you have porosity, if you have some cracks, then only it will initiate from inside. Otherwise, it will start mostly from the surface cracks. So surface roughness is one problem. Surface properties is a problem. Surface residual stress is another factor that will affect these things. We'll see one by one. Surface roughness, you see that. So this is a table will give that. So different measuring process, lathe machine, polished, ground, super finished. The surface roughness value will vary from 2.67 to 0.05. Ground and polished. You see that the fatigue life is very high, 2 lakhs 34,000. But in the lathe form, same material, the lathe machine, just rough machine, it is only 24,000 cycles. Okay, partially hand polished, so it is increased. The life is increased to 91,000. So the surface finish will play a major role. Okay, so if you want to improve the fatigue life, fatigue strength of the material, not fatigue strength, fatigue life of the component, then the component should have the fine finished component will have higher life than the rough finished component. And why it is happening? Because now, as you told know, the surface roughness, there is ups and downs. Ups and downs will act as the stress risers. The crack will initiate easily will initiate from the ups and down valleys. So this is another treatment. So treatment, surface treatment, you have a lot of treatments out there. So this it's not related to the fatigue, but the strength will vary and hardness also vary when you do the surface treatment. So surface properties, if you see here some of the properties, change in surface property due to surface treatment, change in fatigue strength and properties. So some of the reduce the fatigue performance, decarburization, soft coating, electroplating, they all reduce the surface fatigue performance, fatigue life. But treatment improves the fatigue life, fatigue performance, carburizing, nitriding, flame hardening, induction hardening. These are all heat treatment processes used for the steels and carbon steels, and they will improve the fatigue properties because they will introduce the compressive stresses on the surface. If the compressive stresses are introduced, then the life will be more. So whatever the treatment you do, whatever the post treatment you do, if the treatment increases the compressive stress on the surface, then the fatigue life will be higher. So surface residual stresses. So you have no, it's okay. This I'll leave it. I'll come back to this because this diagram will explain you properly. Residual stress, surface residual stress. Surface residual stress. If you see here, this first specimen A, it is the elastic stress distribution. A beam with no residual stress. There is no residual stress. So it is the one side because it's having the tension, and the bottom side you have the compression. This is the case in the rotating beam fatigue testing machine. The stress is varying from plus 200 to minus 200. Okay, plus 200 to minus 200, or equal to minus 1. This is a typical case. So it is elastic. There is no residual stress here. But in the second specimen, you see that there is a residual stress distribution that is produced by the sharp peening. One method, sharp peening, small iron balls, steel balls will hit on the surface. So by doing that, you can introduce the compressive stress. So when you introduce the stress like this, what happens? The pattern is changed here. From the tensile mode, the stress you are having in this specimen, that is when you do the sharp peening. So in the surface, you have the compressive stress field, both top and bottom. Okay, but in the inside you have tensile mode. You have the tensile component is there. So if you relate, if you combine this, okay, so the sum of these two, first and two, if you combine that, what happens? The stress is, the tensile stress is going down. It's not on the exactly on the surface because of the sharpening operation. The magnitude of the compressive stress is reduced on the surface. Okay, reduced on the surface, and it is going inside, just below on the surface, maybe 1 mm below the surface. So by that, the if it is the case, if you introduce that, so this you can improve the fatigue life of that, because the crack will initiate normally from the top surface, but now the maximum tensile stress field is just pushed inside the material. So crack has to initiate from here. So that will take more time than the first case. So that is the effect of residual stress here. And there are many methods available for surface rolling, sharp cleaning, polishing, thermal stresses. They all introduce compressive stresses. Compressive stresses, as I told, compressive stress will close the crack, partially will close the crack. That's why I explained that in the case of the crack initiation itself, it will crack, and the crack growth itself, it will close partially. So it will decelerate the crack growth. So that's why the is beneficial. Compressive stresses are beneficial because it is a pushing, it is crushing the material. When you crush it, when you push it, the crack, whatever the crack it is grown, it will be closed partially. So it will decelerate. It won't stop. Okay, it won't eliminate the crack growth completely, but it will delay the crack, delay the failure. That means what? Delay the failure means what? The fatigue life will be enhanced. Fatigue life will be improved by introducing the compressive stress. Compressive stresses will delay the crack, will decelerate the crack growth, and by that it improves the fatigue life of the component. And metallurgical variables, yes, fatigue strength and the yield tensile strength, there is a relationship, it is called fatigue ratio. Fatigue strength divided by tensile strength of the material. If you do both the tests, no, tensile test and fatigue test, you find out this ratio. That ratio is important parameter, and tensile strength is high, fatigue strength is also high. Okay. And other metallurgical variable, grain size, yes, it has effect. Grain size, especially it is having effect on the high cycle fatigue region. Low stress, high cycle fatigue region, it has the maximum effect. Grain size. Finer the grain size, the fatigue strength will be higher, fatigue life will be higher. Coarse grains, the fatigue life will be lower. So grain boundary, by strengthening mechanism also you can improve the fatigue strength. Grain boundary strengthening, fiber strengthening, second phase strengthening, cold working. There are many strengthening mechanisms are there. So that will also, by increasing the tensile strength, you can increase the fatigue strength. Okay. And improvement by controlling metallurgical variables. Yes, by doing this, as I told you, strain aging, cold working, and these things also will improve. Whatever mechanisms that will improve the tensile strength or yield strength of the material, that will also improve the fatigue strength of the material. Okay, yield strength. Whatever you do to improve the yield strength of the material, the same will be useful for increasing the fatigue strength, because the yield strength is there, as I told you, starting point for testing is yield strength. So below yield strength, if you do the test, the failure will occur. So if you increase the yield strength, then the fatigue limit will be high. Corrosion, again, corrosion definitely will affect the fatigue life. So because now if you see this graph, crack growth rate versus delta K, if there is inert atmosphere, the crack growth rate is slower, but in the corrosive environment, the crack growth rate is faster. Okay, dotted line shows the corrosive environment. This is inert environment. Inert means it's a vacuum. So there is two different environments. Corrosive environment, the crack growth rate is faster. Why it is faster? You see the slope of the curve is higher. M is more the corrosive environment. So definitely they will, because the corrosion will introduce pits. Generally, all the corrosions, what are the type of corrosion? They will introduce the pits first. Pits means what? Removal of material from localized area in micron level pits, micron pits, micro pits. So those pits will act as the notches, stress risers. So from those pits, the crack will initiate. So fatigue crack will initiate. If there is a stress difference, stress gradients, okay, stress rising point, definitely it will initiate from there. Okay, so corrosion is very dangerous for the fatigue. And temperature, again, temperature is also very testing temperature is less than room temperature, it is low temperature fatigue. If the test temperature is greater than room temperature, then it is high temperature fatigue. And if temperature is low, fatigue strength is high. Okay, at high temperature, what happens? No, the fatigue failure will change into creep failure because it's fatigue also it runs for many hours, and creep also no, it will run for many hours. So there is a transition is possible at the high temperature. And thermal fatigue, thermal cycle volume changes from cold to hot. Thermal fatigue is nothing but low temperature to high temperature, cold temperature to high temperature. There is operating temperature. Yesterday I told you somebody asked low cycle fatigue. So low cycle fatigue, it is a cold temperature to hot. Cold means don't think that 0 and minus 0. Even at room temperature, operating temperature is fluctuating from 100 degrees to 600 degrees. Cold is 100 and hot is 600. So the variation, also fluctuation in the temperature, also will cause the fatigue in the material. And yesterday I forgot to tell the dimensions of the fatigue specimen, rotary bending fatigue specimen. So these are the shape of the specimen. So one is the unnotched specimen, the top one, and bottom one is the notched specimen. Total length is 150. Even some machines know you can accommodate 100 mm length. So, but the shape will be like this. The unnotched specimen, the shape will be like that. These specimens are used for rotating the SN curve, for construction of SN curve. And this is the rotating wing fatigue test machine. Again, install make. It's a tabletop machine. So it will hold a small specimens, 10 mm diameter. The dimensions are fixed. 10 mm diameter. Only maximum diameter can hold is 10 or 12 mm diameter. You cannot test more than that. So it will be run for many hours, and finally failure will occur. Here you cannot monitor the crack initiation, crack growth, everything. Nothing can be done. Only the stress you can vary. And for the stress, applied stress, what is the number of cycles to failure? Once the failure occurs, the machine will stop. So there is a counter. The counter will give the reading how many cycles it has run. Okay, so this is the machine. This itself cost we bought some 5 years, 8 years back. It is 12 lakhs rupees from Instan. And the SN curves we did for the. You see why I am showing this curve is. So this line, if you see a lot of SN curves are here. The bottommost one is for the IAW fatigue 1112 for this material. The material is fatigue stainless steel. We did for the 409M joints, unnotched specimen. For that material, the IAW recommends the recommendation is it should have this is the line. So all the joints have performed better than that. Okay, to find this is the criteria you have to meet when you do the welding. The criteria has to be. If no, if all the curves falls below the IAW, the guidelines or IAW fatigue curve, then the joints are you cannot apply in the actual applications. Okay, so to compare that, you have to use this graph. And a notch specimen. This is for notch specimen. So from these two SN curves, one is for.
Sir, sorry to disturb you, sir.
Definitely, I'm completing.
Sir, next slide is it's not moving, sir.
It's not moving.
Yes, sir. Now we are still at the effect of residual stress.
Oh, okay. Okay, I think it's time is up or what? Oh, here only you are having. Hello.
Please, sir. Please tell me, sir.
Yeah, it's now it is moving.
It's not moving, sir. Not moving, sir.
Okay, so I on 10 slides I moved. Okay, so this is the last slide. Can you see now? No.
Yes, no, sir. No, sir. No, sir.
Okay, so I think it's some problem there in the.
Sir, can you
I
share
don't know
the
what's the problem. Yeah. So we will take some questions.
Yes, sir. We will take.
I will take some questions.
Mr. Mani asked one question. Oh, sir, 1 second, sir. Karnavaran asked a question, sir. Is there any method or technique to evaluate the results?
There are many methods. There is destructive methods, non-destructive methods. For destructive methods, there is a method called the deep hole drilling method. They work on the principle of strain gauge principle. And non-destructively, you can evaluate. The best method is non-destructive method. You can use the XRD, this is X-ray diffraction, radiography method. You can use. There's a lot of goniometers are available. So even in Tamil Nadu, even I think many places WRA is having.
Sir, are you able to hear me, sir?
Yeah, yes. Sir.
Please, sir.
Destructively, we can use deep hole drilling method, and non-destructively, we can evaluate using the radiography technique. Methods are available. Radiography technique works based on the Brock's law by using n lambda is 2d sin theta, n lambda equal to 2d sin theta. That Brock's law is used to evaluate the residual stresses. Methods are there. A lot of methods are there. These two are very widely used: deep hole drilling and this radiography method. Hello. வாங்க ஹெச்ஓடி ரூம் வாங்க உள்ள வாங்க.
Yes, sir. Yes.
Yes. Any other questions? I think time is the problem, right?
No, sir. No, time is not a problem, sir. We can run for 2.5 hours in the live. It's not a problem.
Okay.
And sir, shall we take another question?
Yeah.
Sir, is it possible to calculate? Is it possible? Calculate the energy required to propagate the crack, sir?
Yeah, it's possible. No, energy required is nothing but maybe tomorrow I'll take fracture mechanics. There is the energy release rate, and the stress intensity factor is also one of the that is the energy required for propagating the crack. Because as I told, no, the stress intensity factor is the function of the crack length and the applied stress. Okay. So if you multiply the crack length and the applied stress, then you will get the value. That value is magnified by the orientation of crack, geometry of the crack. Okay. So these three: geometry of the crack, the applied stress, and the crack length. So these are the three important things. By using these three values, you can calculate what is the energy required for a crack to grow. The stress intensity factor is one of the parameters. There are many parameters of strain energy density factors, the SCDF. Instead of SIF, stress intensity factor, we have another term called SCDF, strain energy density factor. So these are all now used to calculate the energy required, driving force that is required for crack to grow. Even in the Griffith theory, it will come. Maybe tomorrow I will give some fracture mechanics and touch upon this.
Thank you, sir. Next question. Mr. Kannan asked one question. Any special or advanced sensor are there to measure the temperature during TIG welding?
So the sensors, there are no sensors are there. Mostly now people still use the thermocouple based method. Non-contact type thermocouples have come now. Infrared based thermocouples have come now. Laser based thermocouples have come now. So these are all little bit expensive. Still we are depending on the conventional thermocouple. But this is a laser based, infrared based thermocouples are there. So they will give, you can measure very closely, very accurately. And thermal image cameras have come now. So by taking the thermal image cameras, the thermal images during welding, you can measure the temperature very easily. But they are not very expensive proportions. A thermal image camera, even Kalpakam, IGCAR Kalpakam, they have thermal image camera. And they take the images during welding, and then they will correlate the based on the color profile, the temperature you can measure. It's possible. It's a lot of sensor advanced techniques have come now.
Okay, sir. Thank you, sir. Thank you. And so next question, sir. Is it possible to find out the endurance limit under torsional loading?
Internal?
Endurance limit under torsional loading.
Yeah, it is. It's possible. That require a different setup. Whatever setup you have seen, the fatigue. For fatigue, generally, mostly it is a push-pull type. The actuator is in the push-pull type. Hydraulic actuators normally they use. It is a push the component or pull the component. But torsion you require, it is a evolving one. So that the machines are there. Torsion machines are there. You can evaluate. That. Because that's the loading is different. Torsion means what? You have to twist the specimen, okay? Clockwise and anti-clockwise, you have to twist the specimen. But here, in fatigue, you are pushing and pulling. Only thing is, you have to give the rotate the specimen in the opposite direction. One end is rotating clockwise, other end is rotating in the anti-clockwise. So that they will do many times, and they'll see the how many cycles it is. It is the torsion testing machines are there. Advanced machines have come. Now tabletop machines we are giving for the students. In the SM lab, center metals lab, the torsion testing machines are there. And that is for simple specimen. For complicated specimens, a lot of like even instant machines have come for torsion testing. Machines are there. We can evaluate.
Okay, sir. Thank you, sir. Thank you so much, sir. Thank you so much. I think I'm not finding much more question in the chat box.
Okay.
And thank you, sir.
It's somewhat difficult to follow the fracture mechanics. Even tomorrow, that's why I went very slowly today. It's somewhat difficult to understand the terms, new terms. Even tomorrow, we'll see a few more. Actually, I want to focus more on fracture toughness. How to evaluate fracture toughness? It's one of the important material property, K1C, J1C, and all the things. Before going to that, I will introduce the fracture mechanics concept. Maybe for 15 to 20 minutes, the remaining 40 minutes, I will focus on the fracture toughness evaluation.
Okay, sir. Thank you, sir. Thank you, sir. Then we will meet tomorrow, sir. Thank you, sir. Thank you so much, sir. Thank you. Participant, thank you so much. We will meet by tomorrow.